Do you see that? It's sound activated. So cool. All right, time to study. Yes. It's empty, so you can put it away. All right, guys, we're going to talk about oscillations. So we'll have to go fast because we wasted a lot of time. Maqsadul, actually, not my fault, Maqsadul's fault. Yes, say sorry. Right, let's start. Oscillation. So first of all, you have to understand in oscillations, the specific thing that they want you to know about in A levels is this thing called simple harmonic motion. So simple harmonic motion is this motion that you know about. It's just that you're not aware about it. So I'll just try to point it out for you. So one of the first places we see simple harmonic motion is if you have a pendulum which oscillates back and forth, right? So that's simple harmonic motion. Where else can you see simple harmonic motion? For example, say we take a spring and we put a mass in the spring, we pull the mass down and then let it go. It moves up and down, up and down, up and down. That's simple harmonic motion. Or when you take, say, a long stick and there's this heavy piece of metal or whatever at the bottom of it, and then you throw it into the water. So what's going to happen? It bobs up and down, up and down, up and down, up and down. Or even say a building after an earthquake. If after the earthquake strikes and then goes back again, what are you going to see? You're going to see the earthquake leaves the building shaking from side to side in this sort of manner, right? You see this in many places. You might have this a tree. Maybe you did those tall talgas. Maqsadul talgas.
It's very nice.
Yeah, I know. It's really artistic, isn't it? Let me put a cloud here. One more?
Yep.
Okay.
That's better.
Okay, no more. So yeah, say the wind hits this. What's going to happen? A gust of wind, if it hits it, you're going to see it's going to be, but after one gust, it's going to be moving left and right, left and right, left and right. So these are different types of things which we call simple harmonic motion. And the few different types that are going to come in your A levels a lot. One is this. This comes in a lot. One is this. It comes in one of the most, and also this. And there's this other slight variation of this is when you put a ball in a bowl and then you let go of the ball and it just rolls back and forth, back and forth, back and forth. So first of all, you're going to see something common about all of these different types of oscillations. What is it? These oscillations, these motions have two common properties. Common property number one is they all have an equilibrium position. What's an equilibrium position? Where the object would be if you didn't disturb it. So Maqsadul, can you show me the equilibrium position of all of these systems?
This is in the middle, where it's just hanging.
Yes.
It should be in the middle as well.
Yes, very good. This is going to be at the bottom of the bowl. Yeah.
And this is where it is.
Where it is, most likely if it's the point where it stays without disturbance.
Yep.
Maybe this for this, this for this, and this for this too, right?
Yep.
So equilibrium, all of these systems have an equilibrium position where basically if you didn't disturb it, it would stay there, right? Then what's the next thing? Yeah, basically what's going to happen is, for example, this pendulum. If you move it a little away from the equilibrium position, what happens is it wants to come back to its equilibrium position. If you move it further away from the equilibrium position, it wants to come back even more with greater force. Basically, the resultant force that the pendulum experiences is greater. That is because of a component of weight. Basic component of weight, you have an angle here and a force here. If you move further away, the component of weight increases. Same stuff happens on this side, right? So what we can say is that the acceleration of the particle depends on how far it is from its equilibrium position. Isn't that so, Maqsadul?
Yep.
And it's true for all of them. For example, if I took this tree and if I moved it a little bit, then it would go back slightly, right? And then if I move this tree and then pulled it, I tied it and then pulled it all the way down and I have it tied down to the ground here, like those Tom and Jerry things. Or that Indian movie, what is the name of that Indian movie?
I don't know. But
Come on,
we're
come
talking
on.
about it.
Was it Bahubali?
Bahubali.
Bahubali 2.
Yeah.
Yes, Bahubali 2. So they have this bunch of people who get onto the tree here. But I just seen that part of the movie. I'm not a very big fan of Indian movies, to be honest. And then they cut the cable here, and then they all jump, the tree jumps like crazy, and they all jump, and then they go over the enemy wall, the fort, as a ball.
And then everyone's okay when they land.
So yeah, so they go as a ball, and then what happens is the ball then lands and then bounces. Oh man, you guys need to watch that stuff, man. It's crazy. So yes, that's Bahubali 2. So So basically, the point I'm trying to make here is the further the tree is taken, the more violently it wants to come back to its equilibrium point. So that's basically what? That's what we call acceleration towards its equilibrium point. So simple harmonic motion has these two really simple rules. So what are the simple rules of simple harmonic motion? Number one, acceleration is proportional. Yeah, proportional to the displacement from equilibrium position. Right? That's point number one. But, oh, apparently video quality is dropping.
Is it internet?
Maybe it's poor internet. Maybe. I don't know. But there isn't anything we can do about it, is there? Guys, how's the net now? How's the connection now? Is it alright?
The thumbs up if it's okay.
Yeah, thumbs up, thumbs up. Oh, that's thumbs down. Wait. Thumbs up. We'll have to watch it from here, I guess.
Yeah, thumbs up.
Oh.
Depends on their internet as well, like, you know.
হ্যাঁ কিন্তু দুইজন বলছে দুইজন আলাদা বলছে that's why. Better now. It's okay. It's better now. All right. We're good to go. We're good to go, guys. So yes, acceleration is proportional to displacement from the equilibrium position. And the second point is going to be what? The acceleration is always... My handwriting is getting really bad now.
I think it's that.
My handwriting being bad is not for video quality, Maqsadul.
Video quality, it's your handwriting.
Yeah, sure.
Blame it on my phone.
Yeah, blame it on your phone. Yeah, then what? Blame it on the internet. All right, I'll try to write this nicer. Acceleration is... I don't even know what I wrote. The acceleration is...
Always, that was always.
Oh, yes, always. Always towards the... equilibrium point. All right, so these are the two rules of simple harmonic motion. And in combination of these two rules, we can actually come up with a lot of interesting stuff. So first of all, what I'm going to do is I'm going to take a situation where we have a mass, right? So we have a mass on a spring, and we pull it down and we let it move up and down, up and down, up and down. So if I was to show this motion with time, I could draw a displacement time graph which would basically be this, right? Moves up, highest point, then lowest point, up, down, basically with time. But this is just moving up and down. Basically this would be like this, moves, whoops, up, down, like, okay, I'm trying that, right? It's really hard to do in camera. Usually I'm pretty good at this in class. You know, yeah, like, you know, ooh. Okay, but I'm just losing coordination. I hope you guys get it. Oh my god, Tehzeeb, man, Tehzeeb. He wrote, এখানে যে ভাইরা জানেন না উনি ডাক্তার মানুষ এই লাইভ দেখে বুঝে নিন Yes, yeah, my name is Doctor. Yeah, that's my name. Anyway, guys, let's move on. So basically I can draw this as the displacement versus time graph, right? So now let's go into a couple of interesting points. Number one, if you studied circular motion already, then you should know we can use the concept of omega. This is not W. Please do not call it W. Maqsadul?
Not W.
Yeah, don't call it W. This is omega.
W. I'm kidding, that was a bad joke. I'm sorry.
I should stab you someday. So omega. So omega is the concept of what was it again? Yes, basically we can call it angular speed or angular frequency. Yes. So it's how much of a complete cycle do you complete in a certain time. So one of the easiest ways of showing that is basically theta by t, or you can also write it as 2 pi by t. 2 pi by t. Okay. Samina bro, W. Okay, I don't wanna. I really don't wanna. So 2 pi by t, right? So here, please notice that there's no angle which is going on here, right? What is going on is we're just representing the motion on a sine graph. So the speed at which is passing through the cycle can be represented using omega. There's no angles, and even if it's a pendulum, there's no angles, all right? No angular stuff. What it's going to be is basically sine omega t. So what sine omega t here represents is basically, say, at time t, I want to know if the oscillation is at a certain position or not. So, it's Munim. It's actually Sheikh Munim Tazwar.
Oh, hi man.
Yeah.
Shout out.
A shout out. Yeah. Do you know what he just said?
What he said?
Please stab Maksud. Oh my God. Anyway, no, I can't do that. It's illegal. So coming back to this. So basically what happens is, say at a certain time, I want to know where in the position of the oscillation the mass is. So all I need to do is I just need to put the time into the equation sine omega t. So say if the time value is this, t, then I know it's at this minimum. So how would I know this? By multiplying it with sine omega. So omega has a unit which is radian per second, right? So t, if it's in seconds, then basically we can use that to multiply and find sine in radians. And that can tell us exactly where in the oscillation is the mass at time t. So at the time that I've chosen here, this time, we know that it's at its minimum point. At some other time, it might be up here. At some other time, it might be at some random point here, wherever it might be. So basically, this is what this shows. This is what the sine omega t shows. However, there's a problem with this. The highest value of sine omega t is how much?
1.
Yes, it's +1. Excellent. And the lowest value is how much? -1. So it doesn't really represent the oscillation's true amplitude. For example, this goes up and down by, say, 5 centimeters. So 5 centimeters minus 5 centimeters. So this is what? This is what we call x naught, or our amplitude. If that is the case, then if that's the amplitude, then it's not +1 and -1. The +1 should represent the highest point. The -1 should represent the lowest point. So what we can do is we can just multiply the value of sine omega t with x naught. That's going to give us the position or the displacement in terms of x at time t. I know it's a little complex, but you guys are like A-level students, so you should need to do that. Oh, quality hour drop course. How do we deal with this?
Is everyone facing that?
No,
It
it
could be
says
because of
Samin
their-
Abrar. Samin Abrar.
Could be because of their internet. Because if you want a bufferless continuous stream, that
Uh-oh,
would be-
Mohamedul Islam has her. Okay, we're having drop in quality again.
Is it probably because of the internet?
Most likely it's because of the internet. We need to find a good solution for
Better,
this. Yes.
yeah.
Maybe a more stable internet provider, I guess. We need to figure something out. Anyway, guys, bear with me. We'll just have to work with it. It dropped. Okay, everyone's saying it dropped. Okay.
If
Yes.
you're gonna upload it for it, they could if
Nah,
you guys,
upload ye thake.
it's gonna be the same.
Yeah, grainy thake.
Okay.
That's difficult, isn't it?
Yeah.
আবার ড্রপ করছিল একটু আগেই এখন আবার ড্রপ করছে man you're supposed to say এখন আবার ঠিক আছে এখন আবার ড্রপ করছে okay we're going to get a better internet provider very soon, hopefully tomorrow. Tezib, could you please look into that? And Yusa is online. Guys, can you guys please figure something out about that? We need to figure an answer and solution for this. What I'm going to do now is we only have a few more minutes, so I'll just try to explain as much as possible by talking and less by drawing so that you guys can understand. So what I basically was talking about is I drew a displacement time graph of the motion of a spring, on a mass of a spring moving up and down. And what this shows is basically that the object moves up and down, up and down, up and down, and we can turn that into an equation. The equation is going to be sine omega t, but you have to multiply to the amplitude, so the displacement x is equal to x naught sine omega t.
For displacement.
Yes, for displacement. This is an equation which represents the displacement of the particle with time. So that's number one, right? That's the first thing that we need to know about and figure out. And from there, we can actually differentiate this equation and find out a few more other things. For example, what's the differentiation of distance with respect to time?
Speed.
Speed, yes, or displacement. If it's displacement, is velocity. Very good. So, basically what's going to happen is x naught sine omega t turns into something else. What would it become? If you differentiate it, it becomes v is equal to x naught omega cos omega t. This is what we get if you differentiate it. And let's try differentiating the graph. I'm going to do this thing, but yeah, if there's not a good what should I call it? If there's no good internet connection, it's going to be
a fresh page.
but I need this graph.
Okay.
So basically what I'm going to do is I'm going to slice up this graph, all right? So if I slice it up, I'm going to get different values of the gradient. So for example, here the gradient is a maximum, then it slowly decreases to 0 here, and then becomes a maximum negative here, and then increases to 0 here, and then increases again, and then this thing goes on, right? So yeah, like, you know, bad internet won't let this be a good thing. So as you're going to see, these are points where the gradient reaches 0, right? So these points are here, like this would be a point, this would be a point, basically points where they almost become flat, right? So this would be the differentiation of a sine graph. And if I was to plot a graph against this,